Okay, so we talk about universal hashing. So before that, let us just complete the analysis of open addressing. So analysis of open addressing. So basically, just to recap, so in the open addressing method, we are just having the prop sequence. Here hash function is a function from u cross, this is the sequence number of props to. So we have basically we have a hash table of size m 0 to m minus 1. So when this is the set of keys. Now if we insert a key, so what we do, we just apply the 0th probe. So we apply the 0th probe. So h of k comma 0, and if it is hitting some occupied slot, then we go for the next probe, h of k comma 1. This is the 0th probe, this is one probe, and if it is still hitting some occupied slot, then we go for the next probe, h of k comma 2, and this way we continue until we get a empty slot. Once we get an empty slot, we will insert that value k, insert the k over here. So, and we have seen two example of probing, linear probing and double probing in the last class. So now we will analyze this is called open addressing. So we analyze so everything we have to be feed in the table. So there is no storage outside the table. So we are not allowed to have a linked list outside the table. So chaining is not allowed. So we have to feed everything inside the table. So basically the idea is to search for a empty slot by this probe sequence. So we have a sequence of hash functions. So we have applying first hash function if it is hitting some occupied slot, next hash function like this. Okay, so this is the recap of what is open addressing. Now let us analyze this open addressing by a theorem. So this theorem is telling given an open address hash table with load factor alpha, which is basically n by m, and this has to be less than 1. Why it is less than 1? Because if there are n keys, if there are m slots, if the number of keys is more than the slot, then there is no way we can fit the keys. If there are say if there are 10 slots and if there are 20 keys, then we cannot fit 20 keys in the 10 slot. So we need to have the extra storage there. So that assumption is mandatory. So n is the number of keys and m is the number of slots. So n has to be less than m, otherwise we cannot fit the keys in the table by the probing, because if it is so, this assumption is quite okay. So n has to be less than m. Okay, then the theorem is telling the expected number of probes for an unsuccessful search, the expected number of probes in an unsuccessful search. Unsuccessful search means we are searching a key which is not there in the table. Unsuccessful search, we are searching a key which is not there in the table, is at most 1 by 1 minus alpha. Okay. So, this is a theorem. What this theorem is telling? So, we have n keys, we have m slots, and we have a open address hash function, and we have fill up these keys into the slots by using this open address hash function. And now suppose we are trying to find out a key which is not there in the table. Okay. So, now what is the number of probes we should have? We should do this for this search. So, that is the theorem, and that it is telling 1 by 1 minus alpha. So, how to prove this? Okay, to prove this, we will just use some probability stuff. Okay, so there are, say basically there are m slots 0 to m minus 1 m slots, and in this m slot there are k keys, sorry, n keys are sitting there. Okay. Now, one probe is mandatory. So, one probe is required. So, one probe is mandatory, because so suppose we are finding a key k star which is not there in the table. So, for that we need to try the probe, that is 0 of 0, that is the 0th probe. So, one probe is required. So, if we denote this is the number of probes, so one probe is required. Okay. Now, so when we go for the second probe, if this is hitting to a occupied slot, then only we go for the second probe, I mean next probe. So, now what is the probability that it is hitting to a occupied slot? Now, what is the probability that it will hit to a occupied slot? Now, total number of slot is m. Now, there are n keys live in this here. So, just the classical definition of the probability. So, if we choose one of this, if it is hit one of the slot where this n keys are lies, then that is the probability. So, basically probability that it will hit to a occupied slot is n by m. So, the probability that it will hit to a into a occupied slot is basically n by m, because there are n slot which is favorable case, and there are n slots are there, n keys are there in that slot, and there are total m slots. So, if we can hit any one of this n, so that is the just classical definition. So, n by m. So, with this probability n by m, then we will go for the next probe. So, that means, so we will go for next probe with this probability 1 by m, and then again next probe, then again we will go for the next probe if it is again hitting to a occupied slot, and that probability is basically n minus 1 by m minus 1, and then we will go for the next probe like this, and again we will go for the next probe, it is m minus this probability like this. So, this is the number of probes, or we can say expected number of probes in the probability calculation. Okay. So, now we want to simplify this. So, this is the expected number of probes, for an unsuccessful search is basically this. Now, we can simplify this just by using this fact n minus I by m minus I is less than equal to n by m for all I. This can be easily proved. So, if we use that, so this is basically less than equal to 1 plus n by m, 1 plus n by m, 1 plus n by m into like this. Okay. So, this n by m is basically alpha, this is 1 plus alpha into 1 plus alpha into 1 plus alpha into 1 plus dot 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 dot. So, now we have the expression like this is less than basically 1. So, this is basically 1 plus alpha square plus alpha cube, I mean you can say less than. Now, this is basically 1 by 1 minus alpha, since alpha is less than 1. This is the power series, this is the sum, infinite sum, this is 1 by. So, this is the proof. Okay. So, expected number of proof for an unsuccessful search in a open address hash table is basically 1 by 1 minus alpha. So, what is the meaning of this? So, this is the 1 by 1 minus alpha. So, now suppose our table is half full. So, suppose our alpha is 50%. So, that means our table is half full. Okay. So, if we have 100 slot, suppose there are 50 keys, half full. So, alpha is 1 by half, 1 by 2. So, then what is this value? Then 1 by 1 minus alpha is basically 2. So, that means we need just 2 probes for an unsuccessful search. But what happens if the table is 90% full? I mean this is 1 by, this is 0.9. Okay. So, 9 by 10. If the table is 90% full, then what is 1 by 1 minus alpha? This is basically 10. So, if the table is 90% full, then we need to have 10 attempt, 10 probes for an unsuccessful search. So, this is quite obvious, because if we have 90% full means if there are 100 slot and if there are 90 keys and which are distributed over these slots, then it is almost loaded. Then for a search a key which is not there in the table, we need to have the 10 probes for this. So, this is quite. So, this is the analysis of this open addressing, and it is good in the terms of this handling the collision, because collision will be there. In the hash function, you cannot say you can construct a hash function, there will be no collision, because hash function this domain size is big than the codomain size. So, there has to be collision. So, collision, this is the one way we can handle the collision by using the open addressing. Okay. So, now we will start what is called universal hashing. Or universal hash function. Okay. So, to start this, we will talk about a weakness of a hash function. This came from this weakness of a hash function. Okay. So, suppose there is a competition, you have team A, team B. Suppose IBM came to your place and announced a competition to have a hash function, to build a hash function. So, they are going to use this for their compiler or for their operating system. Hash function is having use in compiler operating system. So, suppose they announce a competition to have a hash function. So, you develop a hash function and team B develop another hash function, and you both submitted the hash function to IBM. So, now what IBM will do? IBM will give your hash function to B and your hash function to team A and ask for a ask to find the set of keys where it is colliding. So, it is always possible to have this, because we know there will be collision. So, if we have time, we can always, so given a hash function H, which is basically function from, so one can always construct a portion of the key where it is colliding, because if you have time you can try for all possible keys and then you can just have this k, which is basically for all values it is colliding into same slot. So, and you have to win the you have to win the competition. So, you obviously will try for all possible key for your opponent code and you will come out with such a key and you will submit this to the IBM that this is the set of keys where my friend's code is not working bad, and your friend is also not sitting idle. So, they are also trying to find out a set of keys where your code is performing bad. So, that is can be possible, because if you know the hash function in hand, then you can try for all possible keys and then you can come with some portion where your code is performing badly. So, this is a fundamental weakness of hash function. So, to avoid this weakness, so one can always construct this H such that H of k is always going to be a fixed slot. Okay. So, huge number of collision. So, now to avoid that, how we can avoid this scenario? How our friend or adversary cannot come with some, input where my code is performing bad. So, this type of thing we did in a quick sort. If you remember, in the quick sort, if you know the position of the pivot element, say in our original version of the partition, we are choosing the first element as a pivot element, and then if we put the minimum or maximum in the first one, then we are always getting the worst case. So, we can, even if we know the position is the third element, third means not third smallest, third position, index third, then also one can put the minimum maximum in the third element always and can get an input, can construct an input where it will give us 0 is to n minus 1. So, if we know the position of the pivot element, then we can have a example where our code is performing bad. So, to avoid that, what we did in the quick sort, we did a randomized choice of the pivot element. So, we choose the pivot element randomly, position of the pivot element randomly from the given array. So, here also we will do the same thing. So, to avoid this, we have to choose a hash function randomly from a collection of the hash function. So, this is the way we can avoid this weakness, okay, because if we choose the randomly hash function, then our friend is not knowing which hash function we are going to choose at the runtime, because this choice is at the runtime. So, nobody can come with some set for which it will perform badly, because we do not know which hash function it is going to choose randomly. So, we have a collection of hash function, we are going to choose hash function randomly. So, that is the idea behind this universal hashing. So, let us talk about this little more. So, this is to overcome this weakness. So, a random choice of the hash function from a collection of hash function. So, that collection has some property. What is that? Suppose we have a collection of hash function, this is say H. So, H is basically collection of hash function, it is a function such that U2. So we have, so we consider set of all hash function, I mean the collection of hash functions such that among this collection, suppose there is a portion which is referred as a bad portion, bad in the sense, now if we choose a hash function from this portion, then there will be collision. That means if H is coming from this, so bad is basically, so if we choose two keys, so this is the key set, if we choose two key x, y, x and y, then if we choose a hash function which is x is not equal to y, if we choose a hash function from this bad portion, then there has to be collision. So that means bad means it is basically subset of H such that H of x equal to H of y for all x not equal to y. So this is the this is called bad portion. That means if our hash function is coming from this portion, then there has to be collision for any two key, any two distinct key. If we choose any two distinct key, then definitely they will be colliding into the there will be the collision. So this is called bad portion. I mean I referred this as a bad portion because it is giving us the collision for sure. Now if the cardinality of bad portion is basically cardinality of H by M, if the cardinality of this set, that means cardinality means number of element in this set, is basically 1 by M fraction of the total, then this collection is called universal collection. Okay. If the cardinality of this bad portion is 1 by M fraction of the total, M is the number of slots, 1 by M fraction of the total, then this collection is called universal collection of hash function. And if we choose a hash function from this collection, then that hash function is called universal hash function. Okay. So now we will talk about why this universal hash function is good. So the bad portion is the 1 by M fraction of the total, then this collection is called universal hash collection, and if we choose a hash function randomly from this collection, then it is called universal hash function or universal hashing. So next we will talk about why this universality is good, why we should take this hash function randomly from this collection. So that is the next topic. Next we will talk about why universality is good. Universality is good. So this we will prove by a theorem again. So this theorem is telling, let H be a hash function chosen uniformly at random, equally likely basically at random from a universal set H of hash function and suppose H is used to has n arbitrary key, n keys into M slot, then given a key x, we have expected number of collision with x is less than n by m, which is basically the load factor, and this is good, because if we cannot expect, we are expecting the number of collision is less than n by m, which is the load factor, and that is good. Okay, so how to prove this? So to prove this, we need to use some indicator random variable. So we choose the hash function from this universal set, universal hash function set uniformly at random. So we denote this indicator random variable Cxy is basically 1 if h of x equal to h of y and 0 otherwise. Okay. Now, what is the probability of Cxy? Is 1, is basically 1 by m, because we are fixing x and it will colliding to this. So we are choosing the hash function from this universal set. So this is our h and this is the bad portion. Okay. And the cardinality of bad portion is cardinality of h by m. Now if we have a x, now if we choose a y which is not equal to x, now what is the probability that collision? So collision will happen if we choosing the hash function from this. So size of this is h by m and size of total is h. So the probability that there will be collision is 1 by m basically, because h by m divided by h, so it is basically 1 by m. Okay, so this is the so expected value of C of x is basically 1 by m. Now we are looking for expected value of C of x, and C of x is basically summation over C of x y, where y is not, y is t minus x. So this is we are looking for, and this we want to show is less than 1 by m. So this is basically we can take the expectation inside. So this is basically expectation of C of x y and y belongs to. Okay, now this is basically 1 by m. So this is basically 1 by m. So this is n minus 1 by m. This is less than 1 by m. So this is the proof. So expected number of collision is 1 by m. So that is good. So expected number of collision is basically n by m. So this is the load factor. So the universal choice is good. So what is the universal hash function? We have a collection of the hash function. Among this collection, if the bad portion is just 1 by m fraction of the total, and then if from this collection, total collection, if we choose a hash function randomly, uniformly, equally likely, and if we use that hash function for our hashing, and then this hash function is called, this choice of hash function is called universal hash function. Okay, so in the next class we will construct some universal hash function. Thank you.